Okay, I am going to share my screen now. Do, do, do. All right. So this is going to be the third lecture. Uh, hopefully, what I'll get through in this lecture are some basic quantum mechanics, not quantum field theory yet, but quantum mechanics on the light front, including talking about one particle states, separation of variables for two particle states, and then I would like to go through the harmonic oscillator as an example problem for a two particle bound state on the light front. Previously, we discussed both the basic definitions of light front coordinates and group theory. Uh, I'm going to jump to the summary slides. Uh, just as kind of a basic review of what we went over the previous few times, we defined what light front coordinates are. We stuck with a convention in which light front coordinates are defined with this factor 1 over the square root of 2 in front of them. It ends up making a lot of calculations more convenient. We chose x plus rather than x minus to be time, basically by fiat. Both x plus or x minus are valid to use as the time variable is x plus. And the canonically conjugate momentum variable to that is p minus, which we identify as the energy. Our four products are linear in x plus and x minus. And because of that, the dispersion relation relating energy and momentum ends up having this nice formula without any square roots in it. The energy is simply quadratic in the transverse momentum, but inversely proportional to the p plus. We also have this various kind of non-relativistic like formulas, but with P plus appearing where the mass would in the non-relativistic formulas, including both the energy momentum dispersion relation, but also we find that three components of the four momentum, P minus, which is the energy, and P perp, are proportional to the velocity in the minus and perpendicular directions, with P plus being the constant of proportionality. Conceptually, we described light front coordinates as giving a description of space-time as we see it, at least in one particular direction, the plus z direction. When you're looking in the plus z direction, everything you see you consider to be the present rather than having happened in the past. Longitudinal boosts, instead of a time dilation formula, give you the redshift and blueshift formulas describing redshifts or blueshifts you actually see if an object is boosted be moving away from you, giving a redshift, or moving towards you, giving a blueshift. And if you do what you would normally call a transverse boost, instead of giving you Fitzgerald contraction, it gives you a Terrell rotation, which is what you would actually observe when an object is boosted to be moving transverse to you. However, we defined a special set of generators called light front transverse boosts, which involved both an ordinary transverse boost and a rotation that counters the Terrell rotation. And that leaves transverse spatial structures invariant. We actually utilize this in talking about, well, we looked at finite boosts as well. We got these very nice formulas. We found that the generators of these light front transverse boosts were nilpotent. Basically, when you take the third power of them, you get zero. So if you want to build a finite boost out of these generators, the series expansion for the finite boost terminates, and you end up getting these really nice formulas for finite boosts that are at most quadratic in velocity, with the quadratic term only appearing in the minus component. So the perpendicular components, you end up with something proportional to velocity, which is exactly why you get these nice formulas that the transverse momentum is proportional to the transverse velocity in the light front. And you get a quadratic velocity term in the energy. And the last summary slide, we went over the Galilei subgroup of the Poincare group. Its algebra is identical to the algebra of the two-dimensional non-relativistic Galilei group, which formally explains all of these formulas that look kind of like non-relativistic formulas, except that we have P plus where we would normally have mass, and we have X plus as our time. Uh, we found that light front time is invariant under this group. That's actually basically how we define the group. And transverse separations are also invariant under this group. Now, in addition to the summary, I also should say that I have fixed some mistakes in the slides, which I'll coordinate with the organizers making the slides, even though they're incomplete for the lecture series as a whole, making the slides as they are so far available. So there were various typos, but there was also actually one mistake. The formula I had for the commutator between rotations around the X and Y axes and the light front transverse boosts, I previously had 0 here. That was incorrect. These generators do not commute. So with that summary out of the way, I will now start on one particle quantum mechanics on the light front. So the starting point is we recall this on-shell energy momentum dispersion relation. The energy is equal to mass squared plus transverse momentum squared divided by 2 times P plus. So with this, we do first quantization. We basically convert our positions. Remember that X minus is a position, whereas X plus is a time. So we turn X minus and X perp into operators, as well as P plus and P perp. And of course, P minus will be an operator too. That's the Hamiltonian, after all. So our operators need to obey canonical commutation relations. For the transverse components, you have a standard looking thing. Commutator of xi and pj should be I times delta ij. For the commutator of x minus with p plus, that's actually minus I instead of plus I. The reason for this is basically that there's no minus sign when you raise or lower indices. So x upper minus is equal to x lower plus, whereas x perp upper minus is equal to minus x perp lower. So there's a difference in sign in the commutation relations. It's not conceptually important, but when you're working out all the algebra, you want to avoid sign mistakes, so it's important to notice this from the start. And of course, you have that the non-equivalent components, say commutator of x minus with p perp, commutator of x perp with p plus should be 0. So in the coordinate representation, if you write a wave function as a function of coordinates, you can basically just convert your 4 momenta to derivatives as usual, with p perp becoming minus nabla perp, p minus your Hamiltonian becoming I times the derivative with respect to your light front time. That's pretty standard. And p plus becoming plus I times the derivative with respect to I x minus. The plus I rather than minus I is a peculiarity that you kind of just have to remember. And you can get a light front Schrodinger equation for one particle, which looks like this. You have mixed derivatives on the left-hand side here, which is kind of a peculiarity. Now, this isn't what people usually do when they're on the light front, and I will very shortly get to what people usually do. So people actually don't usually deal with longitudinal position as a degree of freedom. It is actually something of a wonky variable. It is possible to formulate, but you get some weird stuff going on. So in analogy to last time we discussed that you can define an X perp operator using your transverse boost operator. So transverse boost divided by P plus overall minus sign. It obeys all the expected commutation relations that, well, you should for canonical first quantization. You can actually define an x minus operator in a similar way. However, your longitudinal boosts and your p plus do not commute with each other. If you go back to the summary slide of the Poincare group, you'll find that the you get IP plus, so it's not in the Galilei subgroup. So you need to do this whole two-sided average in order to get an operator that's actually Hermitian. Now, with this, it actually does give you the commutation relations that you need for first quantization to make sense. For instance, you have your Heisenberg equation. The commutator with the Hamiltonian should give you the velocity, and it does. Also, helpfully, x minus defined this way commutes with the other position variables, which I work out in detail on the next slide. For this, it's helpful to recall we've defined x minus using this two-sided average of 1 over p plus and times b minus with an overall minus. There's already a typo on this slide. X perp here should have a minus sign here at the top. And you have these commutators from the Poincare group summary slide. Well, we can put in the definitions of x minus and x perp. Fortunately, on this line, there is not a typo. The minus sign is correctly here. And you can distribute out your sum in the left part of the commutator. You can pull out your overall 1/2, your minus signs cancel, and you get a two-sided average of 1 over p plus and a commutator between your longitudinal boost generator b minus and 1 over p plus times bi. So this commutator is in common between both of these terms, so we can work that out. The first term, we can use the handy identity. Commutator of A with BC is B commutator AC plus AB commutator AB times C. And so break that up. Our first term, the BAC term, you have a 1 over P plus here and a commutator between B minus and BI, which gives us IBI here. For the next one, we have a commutator of B minus with 1 over P plus, which we can use the other handy identity that we've used before. Commutator A with inverse of B is minus, commutator of A with B sandwiched between two copies of B inverse. So doing that, we have our first term with our IBI here with 1 over P plus here. It doesn't matter which side we put on because they commute. From this identity, we have a commutator of B minus with P plus, which gives us an IP plus. We have a minus sign from the minus sign in this identity. So we basically just have IBI over P plus minus the same thing, so we get 0. So our longitudinal position operator does commute with our transverse position operators, which is something we want for somewhat normal looking first quantization. It is much easier to show that you get the required commutation rule between x minus and p plus. I'm going to leave that for as an exercise instead of walking you through it. It's definitely easier than working through this, so that's worth doing in your spare time. So we have a collection of operators. We have transverse position and momentum operators, which we can cast into our coordinate representation, dealing with coordinate space wave functions. An operator in your basis, of course, just becomes a C number. So your X perp becomes a C number, ordinary commuting number, and your P perp becomes a minus sign nabla, as usual. In the momentum representation, you also have for the transverse components completely expected behavior from non-relativistic QM. Your P perp operator in the momentum representation just becomes an ordinary number or pair of two numbers, and your X perp becomes a derivative with respect to P with a plus I here. So very similar to how all three components would behave in non-relativistic QM. However, this does not work for the longitudinal components. You have your x minus and p plus operators, and the coordinate representation, they do behave as expected. X minus becomes just a number, and p plus becomes a derivative with respect to x minus. However, in the momentum representation, well, p plus just becomes a number, as it should in your well, the representation for that operator. Your x minus becomes a derivative plus something else. So we can figure out what this something else is and basically show that you have to have this extra term by looking at the momentum space integration element. So now we're going to talk about, well, completeness relations in momentum. So basically, we define a Lorentz invariant one particle completeness relation. So here we're neglecting spin. Pretend we have a spin zero particle. Uh, your set of all possible states that your particle can be in is then uh, spanned by the collection of p plus and p perp values that are possible. So you have an outer product between a bra and a ket for p plus p perp. You also have an Lorentz invariant on shell condition that your p squared, which in this case is going to be 2p plus p minus p perp squared minus m squared, since that's what the light front metric gives us. This has to be set to 0, p minus minus m, p squared minus m squared has to be 0, p squared has to be m squared. So that's why we put this delta function here. And aside from the delta function, we have a four-dimensional integration over four momenta, which is, of course, always invariant. By examining the delta further, well, we use our standard metric relation that p squared is this quantity here. And then we use the relation for the delta function that if you pull out an overall factor s, then you multiply the delta by 1 over s. So we're pulling out a 2p plus here so that we can write it in the form of p minus minus something in order to do the p minus integral. So the p minus integral is eliminated. We're left with a three-dimensional integral over p plus and p perp. And because we had this 1 over 2p plus pulled out of the delta, we have a 1 over 2p plus in our Lorentz invariant momentum space integration element. This is basically the same way how in standard instant form coordinates you'd get a 1 over 2 times e here instead of 1 over 2 times p plus. But in light front, it's p plus, which is actually really convenient because p plus is an independent variable, whereas in instant form e depends on the three components of momentum that you're integrating over. So inner products in momentum space. If we have a state psi and a state phi, we sandwich one between both of them, and we end up getting a psi is projected onto the momentum value, and we define this as our momentum space wave function. And with phi, we have the complex conjugate of the momentum space wave function. So basically, you take phi times phi star times psi, and you integrate with your Lorentz invariant momentum integral. So, as for what this tells us about the longitudinal position, another typo here. This should say longitudinal position rather than momentum. Since the longitudinal position is Hermitian, we can say that, well, we can put in our completeness relation, and we can say that this matrix element of it is equal to a matrix element with x minus inserted inside of the psi wave function or inside of the phi star wave function, and we can just add a dagger here in the purple matrix element because x minus is equal to x minus dagger. Then using basically then the momentum representation, we're assuming that we get a derivative plus an f of p plus term. Well, we have the green term on the left is going to give you minus a derivative of phi. The purple term here in the rightmost is going to give you plus I times a p plus derivative of phi star, and each of these are going to be multiplied by f and f star. So you basically can shove these formulas into the top line, and you get this bottom line here. So you have different derivatives acting on each of these, but these two integrals should be equal to each other. So the first thing you would do is you shuffle things around. This is the same formula. You shuffle things around so that you get the p plus derivatives both on the same side of the equation. Uh, and they'll both have a minus I or a plus I. So you can use the product rule in reverse and say that this is the p derivative of the product, phi star psi. And you can put both of the f's on the same side. There will be a relative minus between them. So that's going to give you plus or minus 2i times the imaginary part. And then you can cancel out the i's on both sides and you get this formula from rearranging them. You can then use integration by parts to move this p plus derivative to acting on this 1 over 2p plus. So basically it's this 1 over 2p plus that prevents f from being 0. If we were doing non-relativistic quantum mechanics, then we could just use the fundamental theorem of calculus to evaluate phi star psi at infinite momentum. That would be 0, so f could be 0. But it doesn't work out when you have this p plus in the integration element. So using integration by parts, you get a minus sign, you act on the 1 over p plus, it becomes minus times a minus, you get a plus, 1 over p plus squared. So you get an extra 1 over p plus. So basically, your f of p is I over 2p plus, and x minus, you get this. You have to subtract off something proportional to 1 over 2p plus. This is somewhat akin to the Newton-Wigner position operator if you're doing instant form relativistic quantum mechanics, where your position operators would have to get an extra term added to them in the momentum representation. So far we have our operators, which we can write either in a coordinate representation where things look really normal, and a momentum representation where our x minus longitudinal position operator uh, doesn't really look that great. So, because of this, and for other reasons as well, we don't really like working with x minus as a variable. So, a lot of the time, we will work in a mixed representation where we describe a wave function in terms of transverse position and longitudinal momentum. Uh, Not everyone does this. Some people do just, they work in the momentum representation period, which is perfectly fine. But almost nobody works in a pure position representation. If people want to use transverse position, they'll usually mix it with longitudinal momentum. And if you write out the one particle Schrodinger equation in this representation, you get something that is just the Hamiltonian, just the time derivative on the left-hand side. And then on the right-hand side, you have this nice formula that has a transverse Laplacian and a 1 over 2p plus. So this is kind of the simplest form that the Schrodinger equation for one particle can take on the light front. Now, this is without a potential so far. Yeah, Philip.
Yes, good morning. I have two questions.
Uh-huh.
First of all, suppose I start out in instant time and I've got a complete set of states which would be of the form P0, P1, P2, or P3,
Hmm.
P1, P2, P3. And I have them normalized. And I
Yeah.
now transform to light front. What happens to the normalization?
I actually don't know because I've never worked that out.
No, the reason I'm asking is you're assuming a completeness relation for the light front Ketzenbras.
Yeah,
But is that equivalent to the completeness relation for the instant time Ketzenbras, or is it different?
that's a good question. For one particle quantum mechanics, I would assume as much, not 100% sure. But when you're doing quantum field theory, I suspect that's not the case.
Okay, that was the first question. The second question is when we say that an operator is Hermitian, it's
Hmm.
not just sufficient to say that Hij is equal to Hji star. the operator has to be self-adjoint on the ij basis. So when you write the coordinate representation as a derivative, you are presupposing a set of boundary conditions which would
Hmm.
allow you to do an integration by parts and establish hermiticity. So my question is, what are the boundary conditions that you have to use in order to show that the coordinate representation is indeed self-adjoint?
That's a good question and something I kind of overlooked in doing this, but at the very least, I would assume that the state, the wave functions, so the basically the L2 squared functions that you get when you project from your abstract Hilbert space to the coordinate representation, or in this case, the momentum representation. I assume that the wave functions would need to vanish sufficiently quickly at the boundaries of the well, the boundaries of the integration.
Well, yeah, I mean,
So
obviously you would do that. The question is, what are those conditions?
So that would be psi at p plus equals infinity would be zero, and psi at p plus equals zero would be zero.
Okay, well, that doesn't hold for plane waves.
Hmm. Although plane waves aren't actually in your Hilbert space.
That's part of the origin of my question. Yes, plane waves are not self-adjoint. So if you're dealing with the free Schrödinger equation, you haven't yet introduced a potential. Don't you
Right.
don't you have to deal with the fact that plane waves don't belong to a Hilbert space?
I think you would just have to have a wave packet instead of an actual plane wave.
Okay, well you can do that. You can form normalized wave packets out of plane waves. That is
I
true.
mean, technically, you also run into all these issues in non-relativistic quantum mechanics. The plane wave isn't actually in the Hilbert space, so you need to create a rigged Hilbert space and all that. But
Yes.
that goes beyond what I am actually competent to talk about. Like, I don't really understand the rigged Hilbert space formalism, so I can't comment on that in any detail.
Well, if it's any help to you, I just wrote a paper on it.
Okay, I'll have to look that up then.
Okay.
Chung, you had a question?
Yes, I think it might be a related question or comment. I'd like to uh, mention that even in non-relativistic quantum mechanics, perhaps there is a difference between mechanics and field theory. And the reason is that as I understand, in quantum mechanics, there is no time operator.
Right,
So actually, I think Pauli has discussed about the reason why there is no self-adjoint, so-called Hermitian time operator. Uh,
right.
and now this X minus variable is a mixture of time and space. So I'm wondering uh, the same kind of sort of theorem applies because you're using, of course, uh, the normal, uh, the commutation relations, which works in the non-relativistic quantum mechanics, or even if you extend to uh, relativistic version of it. So somewhere you have to assume that the time is an operator in order to derive this X minus formulation.
Hmm. I'm not sure about that because X plus in this case is time, and uh, I'm not postulating that there's an operator corresponding to X plus.
That's right. But X minus or X plus is really the combination of time and space together.
Well, it's a combination of what you would call time and space in instant form, but we're working in light front instead, so we're considering X minus to be space.
But don't you have to think that the instant form dynamics works, and then one can go to the light from dynamics. Actually, there is this formulation that I was working on, the so-called interpolating between instant form and the light from form. And I think this relativistic quantum invariance should sort of make these two extreme forms of the dynamics should give the same physics, I think.
Philip, did you have a comment on this?
Yes, I just want to pick up on what Chungji just said a moment ago. There may be a nice way to resolve this is to work with Feynman-Stuckelberg in the five-dimensional formalism, where you're non-relativistic in the fifth coordinate, but relativistic in the ordinary time and the ordinary space, which you could then make in light front. So you can define a light front for relativistic x plus x minus, but a non-relativistic fifth coordinate, which is Feynman-Stuckelberg. It's a one-particle formulation of quantum field theory, and it actually predates Feynman diagrams. But I think it will do exactly what Chungji was concerned about. That's just the comment.
Well, I hope it can be resolved, because I have this conceptual difficulty to
Yes.
understand. But anyway, it's a comment, and I know that there has been many discussion about the so-called Pauli's theorem, which is stated that there is no sort of self-adjoint time operator, and people have been discussing in what circumstance maybe that can be avoided and so on, but I don't think this has been resolved.
Well, it's correct that Pauli's theorem forbids a self-adjoint time operator from existing. My understanding is that if you had a time operator that had the same commutation relations with the Hamiltonian as P and X have with each other, you wouldn't be able to have a spectrum that's bounded from below, so you wouldn't have a ground state.
That's right. That was one of the reason for this Pauli's theorem. But I think the point is that in the light front, the space and time is really mixture of time and space. So
Well, even with instant form, space and time are really a mixture of time and space in another sense. Whenever you do a Lorentz transformation, you mix up space and time.
that's right. But that's exactly the difference in the light front dynamics, because you're not really taking these different sort of particles have different times. The light from dynamics is not the boost.
Right. But you basically foliate space-time in a different way. But I believe that the resolution to this is you do the space-time foliation first and the quantization afterwards.
That's right. That's exactly the reason why we need the field theory, because quantum mechanically you cannot really have a time operator, but it's a parameter. So therefore, people sort of demote the position from the operator to the parameter. At the level of parameters, time and space can be mixed. So therefore, the so-called relativistic quantum field theory can be established, and that can be worked whether it's an instant form or the light front form, or any in between.
Okay. Thank you for the comment. Was there another comment or question?
I think the hand was lowered, so we can proceed.
Okay. So next, I kind of just had a basic thing on Fourier transforms for, I guess, concern about time, I won't go into too much detail. Just note that whenever you're doing any kind of Fourier transform, you need to be mindful of the 1 over 2p plus in the relevant integration elements. And you can Fourier transform over just the transverse or just the longitudinal degree of freedom. And if you're mindful about your normalization, then you end up in the mixed representation. This will be important later, that the normalization of a wave function in transverse position and longitudinal momentum at the same time has a 1 over 4 pi p plus in the integration element. So the summary so far is just, well, the list of operators in both the coordinate and momentum representations, along with this normalization rule in the mixed representation. And basically nobody works in the x minus coordinate representation. At least I haven't seen any papers where people are doing it. So the next thing I want to go look at is light front quantum mechanics, still not quantum field theory, with two bodies and separation of variables for that. So I'm going to look at a really elementary review first, separation of variables for non-relativistic two-body systems. You define a barycenter being a center of mass by weighting the positions of your two particles by their respective masses and dividing by the total mass. And you have a relative separation defined as basically the difference in positions of the two particles. You can derive canonically conjugate momenta for them, the total momentum being conjugate to the center of mass position, and this relative momenta where you have kind of switched up masses m2 times p1 minus m1 times p2 as the relative momentum. And you can prove that these are the correct formulas by requiring that your relative variables and your center of mass or barycentric variables obey the canonical commutation relations, and that the degrees of freedom actually separate. So transverse separation and total momentum should commute. They do. Similar for a relative momentum and barycenter. You have your transformation formulas, which can be inverted to get the positions of the actual particles in terms of the barycentric and relative positions, similar for the momenta. And the main perk of doing this is that you get a clean separation of the Hamiltonian into a barycentric part and a relative part. So if you write out the kinetic terms, non-relativistic, and a potential that depends only on the separation, then you break it down into a free Hamiltonian for barycentric motion and an internal structure that is independent of the barycentric motion in terms of a total mass and a reduced mass. Separation of variables for the transverse component in the light front proceeds similarly. You define a barycentric transverse position, but using P plus instead of the mass. So the barycenter on the light front is a center of P plus. And you have a relative separation that's just the separation between the transverse coordinates. You can define canonically conjugate transverse momenta. One of them is total momentum. One of them is a relative momentum, again, with the switched up, say, P2 plus times P1 perp minus the other. And these can again be proved by requiring that the canonical commutation relations hold. You can also invert them, just like with non-relativistic quantum mechanics. The question then is, what does this do to the light front Hamiltonian? Well, start working it out. We have our terms from our dispersion relations for the free energy of the two particles, and we have an interaction Hamiltonian, which I put in kind of a dark green here. You can start working it out. Your mass terms end up having this kind of complicated mixture. And for your momentum squared terms, the algebra works out identically to the non-relativistic case. So you're going to have a big P perp squared, total transverse momentum squared over a total P plus, and so your relative momentum squared over something that you could choose if you wanted to define as a reduced P plus, and you have your interaction term. However, in contrast to a reduced mass, instead of defining a reduced P plus, we define momentum fractions. So we use our total P plus as usual, but we have P1 plus divided by total P plus. I'm writing here as Xi1. Nearly everyone uses X for the momentum fraction, but in these slides I'm using Xi instead to just avoid confusing it with coordinates since I'm using X for coordinates in a lot of places. So using your momentum fractions and doing some minor rearrangements of the formula at the top, you can write your m squared of your system as a whole. So basically you can multiply everything by 2p plus, big P plus, and move over the p perp squared to the left-hand side. Well, this is your dispersion relation for your system as a whole. So you get the mass squared of the system as a whole is equal to a bunch of stuff that will now give you internal structure. So you have in light green these three terms. In dark green, you have two big P plus times your interaction P plus, which we can define as V. We can define this product as being our light front potential. The left-hand side is Lorentz invariant because it's m squared, so that is a Lorentz invariant combination. This is literally just big P mu contracted with the light front metric. But we also know that we can get to any big P plus and big P perp from rest. There should actually be 1 over square root of 2 here. But we can get from rest to any state of barycentric motion through Galilean boosts. This means that the right-hand side must be independent of P plus and P perp as well. So the free Hamiltonian part of it, the part that isn't our interaction term, is actually already invariant under the Galilean boosts. Now, technically here, P minus is the light front energy, but a lot of authors, people like Brodsky and Berry and others, refer to big M squared as the Hamiltonian. It's something that you solve for the eigenvalues of. You use a lot of the tools of traditional quantum mechanics. So it kind of makes sense to call it the Hamiltonian, even if it isn't actually literally the energy. Now, the left-hand side commutes with the entire Poincare group because, of course, m squared is a Poincare invariant. That means that whatever the free part commutes with, the interaction part must also commute with. And it turns out that the free part commutes with all of your Galilean boosts. So in one example, for the transverse boosts, you can show using some basic algebra that the relative transverse momentum commutes with transverse boosts. You can use this standard commutator of AB with C relation to break it into two terms, one of which vanishes because, well, you're commuting with momenta with each other, and one of which vanishes because of separation of variables. We have a total X perp with a relative K perp. And you also have that these momentum fractions commute with transverse boosts basically by definition because transverse boosts leave plus components invariant and these Xi's are ratios of plus components. Similarly, you can show that longitudinal boosts leave the free Hamiltonian invariant. For one part, it's helpful to recall that when you do a longitudinal boost, it basically just scales the plus components as well as the minus components in opposite ways. So if you take the ratio of two plus component variables, so P1 plus over big P plus, it's going to be invariant under these longitudinal boosts. You also have that K perp, the relative transverse momentum, is invariant under longitudinal boost because longitudinal boosts leave transverse components alone. So the free Hamiltonian it commutes with all of your light front boosts. That means that the interaction Hamiltonian must also commute with boosts. So whatever the interaction Hamiltonian is, whatever variables it depends on, you need to build it in a way that commutes with boosts. And that gives you some restrictions on what kinds of variables you can use. So first, we've already seen that the momentum fraction and the transverse momentum are already good variables to use in building an interaction potential. The transverse separation also works. You can show that it commutes with boosts. With the boosts, you use the total x perp because a boost affects everything. So you can write this out in terms of its definition. This should be p plus to the minus 1 here. No, that's right. It should be p plus because x perp has the minus 1. So it's times p plus. So you use this AB comma C relation to break it into two terms. One of these terms is 0 already just from variable separation. Your big P plus you can break down into P1 plus and P2 plus. But basically, because these are different directions, your P1 plus commutes with your R perp. So does your P2 plus. So these commute. And of course, because it's a transverse component and longitudinal boosts leave transverse components alone, the commutator with the transverse boost is also 0. What about longitudinal separation? If you take your instant form z coordinates and you take the difference between them, then you'll have a difference in light front times and a difference in x minus positions. Now, when we're describing a state in light front, we're describing it at a fixed light front time. So we just set the x1 plus and the x2 plus to the same value. And at fixed light front time, the transverse separation will just be a difference in x minus variables with a 1 over square root of 2 here. Now, it's convenient that it commutes with x perp because they're independent components of position, and you can show that this commutes with p plus as well with the aid of the canonical commutation relations. However, it is not invariant under longitudinal boosts, and therefore isn't a good variable to use on its own. On the other hand, what's sometimes called the Miller-Brodsky variable z tilde, which is basically this separation times p plus, this is a good variable. And it works out basically because your minus components and your plus components scale in opposite ways when you do a longitudinal boost. So this extra e to the minus eta you get in x minus is canceled by an e to the eta when you boost p plus. So this is it's basically kind of the canonically conjugate variable to your momentum fraction. So we have a list of good variables to use. We can either in the momentum representation use k perp in our momentum fraction. Our two momentum fractions are constrained to add up to 1, so we typically just choose one of our particles and for the two-body case, use its momentum fraction as a variable. Or in the position representation, we can use the transverse separation and the Miller-Brodsky variable. Now, we already have this nice canonical commutation relation between R perp and K perp, one that allows us to write K perp going to, there's an I missing here, in the coordinate representation minus I nabla. Is there a similar relationship between xi and z tilde? In particular, can z tilde be casted to something that depends on derivatives with respect to xi? And that's what the next few slides will be. This will be kind of a dry derivation. If you recall, the total momentum is, of course, just the sum, and your momentum fraction is you take one of your momenta, P1 plus in this case, divide by the total momentum. So your x1 minus and x2 minus in the momentum representation have these peculiar forms. You have your derivatives with respect to p1 plus or p2 plus, but then you have to add something proportional to 1 over 2p1 plus or p2 plus. Well, you can turn this derivative with respect to p1 plus into derivatives with respect to p plus and xi using the chain rule, and you can use these formulas to work out the appropriate derivatives and substitute them in. And you get these kind of inelegant looking formulas. And when you take the difference, you end up getting rid of the derivative with respect to total p plus. So there's an overall 1 over p plus here, and you have a derivative with respect to psi, with respect to your momentum fraction, and then minus this function of momentum fraction. It's actually possible to show using a few simple calculus tricks that you can actually rewrite this in kind of a nice compact form by putting a peculiar function inside your derivative. Basically, your Miller-Brodsky variable acting on a function of momentum fraction is going to be equal to this I times the square root of xi times 1 minus xi. You have a derivative of your original function, but divided by the same square root of xi times 1 minus xi. So it's a bit of a handful, but you can write this invariant substitution for a longitudinal separation, this Miller-Brodsky variable, in terms of derivatives with respect to your momentum fraction. So the way that another important thing for what follows, I was hoping to actually get through the next section in this lecture, but I'm pretty much close to out of time as is. But I guess now for the next lecture, this normalization rule will be important. So recalling that our normalization rule for the mixed representation has in terms of just the wow, there are two typos here. In terms of longitudinal coordinates, it should say. Your longitudinal momentum normalization has 1 over 4 pi p plus. So if you do a Jacobian transforming to total p plus and momentum fraction, you will find that your momentum space element involves you have a 1 over 4 pi big P plus, which makes sense. So this integral here should equal 1. And you end up getting a momentum fraction times 1 minus the momentum fraction in your momentum space integration element for your xi dependence. So this is actually going to be really important for the next lecture. So the summary so far, and I should probably end on this slide because there's only 6 minutes left. So big M squared. So you basically have the big P squared, 2p plus p minus p perp squared, is typically used as the Hamiltonian for solving eigenvalue problems and getting the spectrum of your system. Capital P here signifying the total floor momentum of a composite system. The kinetic and potential energy parts of this are separately boost invariant. Throughout the lecture, I've looked at a two-particle case, but this actually generalizes to any fixed number of particles. So you'd write with your m squared minus nabla squared divided by momentum fraction per particle and add up the particles. Your light front potential here needs to be boost invariant too. We typically parameterize wave functions in terms of momentum fractions. Most authors use x instead of xi. I just use xi here to avoid confusion with spacetime coordinates. And your wave function normalization for two-body systems for the internal dependence has a xi times 1 minus xi in the denominator of the integration element. You can also see formulas that look like this with such a integration element in papers by Frankfurt and Strickman when they're looking at light front distributions of nucleons in the deuteron, for instance. So this is actually a pretty standard thing to see. I'm pretty much out of time, so the third section I prepared for this lecture will have to wait until next time, but I'm open to more comments and questions for now.
Thank you, Adam. Before we go to questions, do you have a preference for when you would like to present the fourth lecture? Next week or in 2 weeks' time?
I think I would prefer 2 weeks' time. I think that the 2-week pace gives a bit more breathing room for also continuing to work on my research and whatnot.
Okay, sounds good. Cedric, you had a question?
Yes, hi Adam. Thanks again
Greetings.
for this very nice series of lectures. I enjoyed them very much, and so I'm very happy that they will continue. I've a remark or maybe a suggestion regarding the X minus component on the light front. So at some point you notice that there are many places where things become complicated because you have this f of p plus function and all that. And I think
Yeah.
you can get rid of these just as people did in non-relativistic quantum mechanics. So instead of having a Lorentz invariant measure, you use the non-covariant measure. You can also do it in light front, so absorb a square root of 2p plus in defining the Fourier transform for momentum space and position space, and you can get rid of many of those annoying terms, I think.
I
I haven't
think that
worked
would
it out,
work
but I think that
actually,
would
yeah.
work. Yeah.
I think that would work actually. Uh, that probably would be helpful for some applications. Uh, Mostly the reason I went through the exercise of the X minus operator in this case was I wanted to arrive at the formula I got for the Miller-Brodsky variable. But what you suggested is probably far more reasonable than working with that X minus operator. That's a good point.
Thank you.
I don't see any other hands raised, but Philip,
Philip.
go ahead.
Okay, first of all, a question and then a comment. The
Mhm.
question is this. If I just work with ordinary electrodynamics, the vector potential is the fourth component of A0 is the fourth component of a four vector. It's not a scalar. So
Right.
how do I deal with this formula, with this VLF, which is not going to be boost invariant, if you were just doing the Coulomb potential? So what happens?
So VLF in this case is actually uh, 2p plus times an energy.
But and that one gives the standard Coulomb energy for the hydrogen atom?
I actually have no idea. The only thing I've been able to work out in this formalism is the harmonic oscillator, which is the next thing I have prepared. Uh, I feel like working out the Coulomb potential would be really hard because, well, you have 1 over R. If you were to try to cast that into light front variables, then if you were to go to the rest frame where you would assume that that should be a valid formula, of course it won't be boost invariant. Then you would have 1 over square root of transverse separation squared plus something times the Miller-Brodsky variable squared. So you'll end up having something that becomes a derivative with respect to xi and a square root in a denominator.
Okay.
It would be
Well,
really complicated.
well, at least you're going to show us next time that you get the right energy levels for the harmonic oscillator.
I get a formula, at least.
Oh, you don't get m plus a half h bar omega?
Uh, I get something that depends on some quantum numbers, and I haven't tried casting them into
Okay.
the
All
usual
right.
quantum numbers.
No, but I mean, this is a serious issue if what you regard as the harmonic oscillator in light front would be not what people regard as the harmonic oscillator in instant. I mean, I think that would be
Hmm.
an interesting distinction and potentially a testable one if that were to be the case.
I think that's a good point.
Yeah.
I guess I could also take the 2 weeks to work through the comparison as well.
Well, I'm not asking you to, but that'd be better. Very nice. Okay, now for the comments.
Mhm.
They're related to the comments by Chungi a moment ago. He's absolutely correct. In non-relativistic quantum mechanics, time is a parameter
Yeah,
and X is an operator. Now, the standard quantum field theory is to demote X to also be a parameter.
right.
That's what we usually do. The
Mhm.
Stuttelberg approach is to promote time into an operator so that time and space are all operators. But then you need a parameter, which is no longer time, and that's the fifth dimension. And so the Feynman-Stuckelberg goes the complete opposite direction, namely, it promotes time into an operator rather than demoting space into a parameter. And I don't know whether anyone's ever looked at light front from the perspective of Feynman-Stuckelberg. Maybe the fifth component would have to be something like the X plus operator or the fifth five-dimensional version of X plus. That might be interesting. That's first comment. The second comment is where do where do plane waves belong if they don't belong in an ordinary Hilbert space? And the paper that I've been wrote recently, it argues the following, that a delta function, either you can take it to be a distribution, which is the standard approach, or you can write it as a contour integral. And so what I'm arguing is that plane waves have to be described by motion in the complex plane and not just ordinary derivatives along the real axis. And the way to see this is we all agree that we write the theta function as a contour integral, the integral d omega e to the I omega t over omega plus I epsilon. Well, if you take its derivative, you get a delta function, and therefore the delta function must be a contour integral too. And so I think that really, if you want to do plane waves properly, which is back to the whole issue of self-adjointness, you do need to go into the complex plane. But as
Mm.
long as you're working with bound states, then everything is fine. Then you're in a regular Hilbert space. You don't have to worry. And so, if you wanted to study charmonium, you would look at the bound states of charmonium as a Schrödinger problem, and it's completely consistent in light front or in instant, or at least it should be. And anyway, those are the comments.
Thank you for the comments.
Okay, we don't have any more hands raised. So thank you. Thank you, Adam, for another enjoyable, illuminating lecture. And this lecture is being recorded. As mentioned, I'll post the place where you can find it. It's at the usual place. And eventually the slides will be posted as well. I think Adam wants to fix all the errors, all the typos.
Yeah, I'm gonna fix the typos and then send them over to you.
Sounds good. So thank you, Adam, once again. Thank you, everybody.
Thank you.
We'll reconvene in 2 weeks' time at the same time. Okay, bye-bye.
Bye.